Okay, now we consider again the last exercise we did in R concerning factor analysis, and we conclude this exercise. I go to the usual working folder, and my working folder, I, as usual, open the file, the txt file with all the commands we created up to now, and select the setwd command in order to set the working directory in the working folder. I selected the command, Ctrl+C. I can close the file from Notepad and go into my R environment, opening the R software. Okay, let me change the size so you can see properly. Okay, I paste the setwd command, Ctrl+V, press enter, and now the working directory is the one I wish. File open. To open the txt file from inside R, I change the data type, all files, and now I can see and select the R commands txt file. Open. Now I can change the commands from inside the R environment. I can change and add new commands and change the existing ones in the txt files, so I can update the txt files and use it to run the previous and the new commands in my R environment. So let's go to the exercises concerning factor analysis. Okay, I'm almost there. The lot of exercises about cluster analysis. Okay, we are here. So the problem is the one you can see here, evaluation of customers about urban bus service according to 5 different aspects. The aspects are cleanliness, punctuality, network coverage, seats comfort, and timetable. The evaluations about these 5 aspects are represented by variables clean, punct, and cov, conf, and time, respectively. And now we can run again the command created last time in order to start to recreate the same data processing, the same output, and start from the same point where we finished last time. So as a first, let's input the data to variables clean, punct, and cov, conf, time. I select all the commands and also the commands k equal to 5 because k corresponds to the number of variables. Control R, and all the commands are selected and all the outputs, provided. So the length of each vector is 20. So 20 is the number of customers. In other words, the sample size. 5 is the number of variables, as I said. Let's create the matrix of the data, so the data set. I remind you that we don't need a data frame here because all the variables are numeric. So all the variables, they have the same data type, numeric. So a matrix is enough for us. The data frame is characterized by the fact that some columns or some variables can be of a different type. So not all the variables, not all the columns must have the same type. So x equal to matrix, we list all the columns, all the variables. We indicate the number of columns, n that correspond to the length of the vectors of the variables, 20, and n col, the number of columns is 5k. By row is false because we listed the values by column. Select Ctrl R. So this is the data set. If we want to give variable names, we can use the call names command, Ctrl R. Now the data set is presented by denoting each column with the corresponding variable name. The multiplot is a good idea at the beginning of our study because the multiplot, in other words, the multiple scatter diagram between all the possible pairs of variables, all the possible couples of variables, is important in order to see the relationship between variables, in order to see whether the variables are, the original response variables are highly correlated or not. I remind you that correlation is important in factor analysis and in principal component analysis because highly correlated variables are variables that provide less information than lowly correlated variables, variables with low correlations, because when two or more variables are highly correlated, it means that the marginal information provided by each variable is lower, because when variables are highly correlated, it means that one of them can be predicted as a function of others. And so it means that when two variables are highly correlated, so that one of them can be obtained as a function of the other, it means that we need just one of them, because with a linear function that can predict the values of one variable as a function of the other, we can get the values of the second variable, and so we just need one of the two variables and not both of them. That said, this is the pairs command in order to represent the multiple scatter diagram. I selected the command and pressed Ctrl R as usual. According to the multiplot, you can see that maybe we have a higher correlation between punctuality and network coverage, maybe. High correlation between network coverage and time, maybe, according to the plot. So the higher the tendency of the dots to be located on a straight line, given the linear direction, the higher the correlation between the two variables, and the higher the opportunity to predict with small errors the values of one variable as a function of the other. So this is a descriptive analysis. Also, the computational correlations is a descriptive analysis, but at least we can quantify the linear dependence between variables. So let's select the core command, Ctrl R, and these are the correlations of X, correlations between each couple of variables. So we have some positive correlations, some negative correlations. I see negative correlations between cleanliness, punctuality, and network coverage. Cleanliness, punctuality, network coverage, time, between punctuality and comfort, between network coverage and comfort, And between okay, if I remind you that the matrix of correlations is symmetric, so we just needed to consider what happened over the main diagonal, because the information provided under the main diagonal is the same, because the metric is symmetric. High correlation between punctuality and network coverage, as supposed, between cleanliness and comfort, between the network coverage and time. The other correlations, positive or negative, are less evident. The values are lower. After that, I told you that an important step, I remind you that an important step in factor analysis, both factor analysis and principal component analysis, is the standardization of variables, so the transformation of the original variables into new variables with mean equal to 0 and standard deviation equal to 1. Variable minus mean over standard deviation. This is the standardization of a variable. And you can get the standardization of all the variables, so all the columns of matrix X, our data set, with a scale command. So Z equal to scale of X is the command in order to standardize all the columns of X. Control R to run the command, and the result is a new matrix, the Z matrix, with standardized values. So each column, each standardized variable has a mean equal to 0 and standard deviation equal to 1, or equivalently variance equal to 1. In order to check this, we can run these commands. We can compute the mean of Z1, 1 as a column coordinate, or equivalently, since we have attributed the columns, we have denoted the columns with the names, the variable names. You can use, instead of the column coordinates, you can use the variable names. So clean is the column, the variable corresponding to the first column, cleanliness, standardized because it is in matrix Z. With a round command, you can represent the means with the 3 decimals. Control R. It is evident that all the means are approximately equal to 0. So the first property of the standardized variables is satisfied. Let's see what's the standard deviation value for all the variables. Select Control R. All the standard deviations are equal to 1. So actually, all the variables in Z are standardized. Now, we performed factor analysis with the factanal command in order to find 2 factors. So we established that we wanted 2 factors. So we ran a factor analysis on matrix X. With the factors argument, we indicated that we want 2 factors. No rotation of the factors at the moment, and regression as a method to compute the factor scores. So the values of the common factors, the 2 factors that represent the output of our factor analysis. So in other words, we want to reduce the dimensionality of the data set from the point of view of the number of variables. You know that the evaluation of the customers is a multidimensional phenomenon, because the evaluation is done considering 5 different aspects, but maybe we suspect and we want to find this as an output, that the same information about the satisfaction of the customers can be represented with a two-dimensional data set. So that basically the multidimensional satisfaction can be summed up with just 2 dimensions. So 5 are too many. We can reduce the satisfaction to 2 dimensions. Let's see if it is true and under which conditions this is true. So I attribute the output of the factor analysis to the FA object. FA object with the factanal command, Control R, and let's see the attributes of FA, Control R. I remind you that the attributes of FA, the main attributes are loadings. Loadings represent the factor loadings of the factor analysis. I remind you that the loadings are the coefficients of the linear combinations where the original variables are expressed as a function of the factors, of the common factors. Uniqueness is consists in the variances of the unique factors. Metrics of correlations are included in the correlation attribute. Factors correspond to the number of factors indicated in factor analysis. Scores represent the factor scores. So the values of the common factors in factor analysis. These are the attributes of FA. So if we want to assign the scores, the factor scores to the object F, you can run this command, F equal to FA dollar scores, and then type in F and Control R. You can see the scores of factor 1 and factor 2. Okay, 2 factors because this is what we asked. If you want 3 factors, you can change the argument factors and put it equal to 3, and so on. So these are the factor stores in this unrotated factor analysis. What about the loadings? So let's select the command where we attribute, we assign the loadings as attribute of FA to the object lambda. So lambda is the matrix of factor loadings. Control R. This is the matrix of factor loadings. This is a 5 times 2 matrix. Each row corresponds to one original response variable. So we have, I remind you that we have 5 response variables, and each column represents a common factor, factor 1 and factor 2. So the loadings are the coefficients of the linear combinations where each observed variable, which original response variable is expressed as a function of the 2 factors. So the coefficients that of the equation where cleanliness is a function of factor 1 and factor 2, and that corresponds to factor 1 is minus 0.848. The coefficient corresponding to factor 2 for the equation about cleanliness is equal to 0.525. So cleanliness is equal to minus 0.848 times factor 1 plus 0.525 times factor 2 plus unique factor plus, okay, the mean value is always 0 because now we are working on the Z variables, so the standardized versions of the original X variables. For punctuality, same. Punctuality is equal to 0.599 times factor 1 plus 0.270 times factor 2 plus unique factor for punctuality, and like that, and so on. The loadings represent the coefficients of the linear combinations of the where the original response variables are expressed as a function of the factors, but also the correlations between the original response variables and factors. And this is what we prove when we compute all the correlations between each original response variable and each factor. Let's select the core commands, Control R. These are the correlations. So the correlation between cleanliness and factor 1, here denoted as a first column of matrix F, is equal to minus 0.8497. Let's go back and see the loading corresponding to cleanliness for factor 1. Here, these are the loadings. Cleanliness factor 1 minus 0.848. Okay. More or less, there is an approximation, but approximately it corresponds. Correlation between cleanliness and factor 2, 0.527. Loading of cleanliness with respect to factor 2, 0.525, approximately same value. Correlation between punctuality and factor 1, 0.6. Loading of punctuality with respect to factor 1, 0.599, so approximately same value, and so on. So correlations correspond to factor loadings, or in other words, the lambda values, the loadings, represent the correlations between original response variables and factors. Let's define the matrix, the 20 times 2 matrix of unique factors. Unique factors are represent the differences between the observed values of the original response variables and the values computed with the linear combinations of the factors. So if X, or equivalently Z, is a 20 times 5 matrix, each column corresponds to one variable and each row corresponds to a statistical unit, in our example the customers, U is also a 10 times 5 matrix of unit factors. As a first, we created a matrix. I put 0 values inside the matrix, the n times k matrix, because I just need to initialize to create this matrix. Control R. Then I compute the difference between the observed values of the standardized variables, so Z, minus the linear combinations of the factors where the coefficients are the loadings. The linear combination can be computed with matrix algebra command as a product between F and the transpose of lambda. F is a 20 times 2 matrix, 20 customers, 2 factors. Lambda is a 5 times 2 matrix, 5 original response variables, 2 factors. So I need to compute the transpose of lambda in order to make the product between f and lambda possible. Select Control R. So these are the values of the unique factors, variable by variable. Now, as I said, the unique factors are variables with the mean equal to 0. The standard deviation so is not can be different from 1. Can be a different value. So the unique factors are not standardized variables. Let's select the computation of the mean values for each of the 5 unique factors, and you can see that by considering 3 decimals, the means are equal to 0. All of them are equal to 0. And then let's compute the commonalities. The commonalities, I remind you that the original variables, since we work with the Z standardized variables, are they have variance equal to 1, and so the commonality is the proportion of this variance explained by the factors, and it corresponds to the sum of the squares of the loadings of the corresponding factor. So the commonality of the cleanliness can be computed with this command, select Control R, and it is equal to 0.995. The sum of the squares of the loadings which correspond to clean. In other words, the sum of the squares of the values in the first row of the lambda matrix. Again, U1, sorry, is the unique variance, and it corresponds to the variance of the unique factor which corresponds to cleanliness, Control R, and it is very small. Let me select U1, Control R. You can see that it is very, very small, 5 times 10 to the power of minus 5. So the sum of H1 and U1, commonality and the common variability, must be approximately equal to 1. And this is the case here. Approximately it is equal to 1. In other words, to the variance of the variable cleanliness, in this case standardized, so of course the variance is equal to 1. We do the same for the second variable, punctuality. The commonality H2 is equal to 0.431, smaller, for sure smaller than the commonality of cleanliness. So the two factors do not explain a great amount of information concerning the evaluation of punctuality. Anyway, let's compute the unique variance, U2, Control R. As a consequence of the slow value of H2, the common variance is high, 0.566. And again, let's prove that H2 plus U2, the commonality for punctuality and the unique variance for punctuality are approximately, so this sum is approximately equal to 1, and this is the case. Let's do the same for H3. Select Control R, the commonality is 0.995. So the two factors explain a large amount of the variability of NCOV, the network evaluation of the network coverage, and the sum of the common variance and the commonality, the unique variance and commonality, is approximately equal to 1. Let's go on with the H4. H4, the commonality of comfort is equal to 0.387. not very large, not very great, and the sum of the commonality plus the unique variance is equal to approximately 0.997. Again, let's compute H5, Control R, 0.569, so also the commonality of time is not very high, and the sum of the commonality and the unique variance is approximately equal to 1. So we arrived here last time, and we start from here. What I wish to do now is to perform again the factor analysis, but with a rotation of the factors in order to improve the interpretation of factors. Let's go back on the lambda values. Okay, this is the lambda matrix, okay, the matrix of the loadings. Since all the loadings are far from zero, for example, for factor 1, you can see the loadings are minus 0.848, 0.599, 0.851, minus 0.490, 0.712. So all of them are quite far, quite not so close to zero. So it is evident that factor 1 is negatively correlated with cleanliness and comfort. So with evaluation for cleanliness and comfort, positively correlated with punctuality, network coverage, and time. So the interpretation of factor 1 is not so easy because too many correlations are far from zero. For factor 2, maybe the situation is different, but again, the loadings are quite far from zero. So we can do a rotation of the axis in order to change the factor loadings, but to find another solution in terms of loadings and factors that maybe explain the same amount of total information or total variability, but with a better interpretation of factors, because since the goal of the factor analysis is to replace the original response variables with the new variables that explain the same amount of information, or at least a smaller but not too small amount of variability or equivalently of information, but a new set of variables with represented by a lower number of variables, 2 instead of 5. So let's repeat the analysis. The easiest way to do this is to copy and paste the previous command and adapt to the new data analysis the commands. So let's start from here. Perform factor analysis. I select all the commands and then I change step by step all of them. Ctrl C to copy, Ctrl V to paste. So let's perform a factor analysis to find two factors with rotation now. So let's change without with. And the command is again fact anal. So let's assign the output of factor analysis to the object FA. Sorry, but in this case, the original matrix of observed variables or response variables is X again, the number of factors 2 again. The rotation now is Varimax. So let's perform the varimax rotation. Okay, nothing has changed of all the other arguments. Let's select the fact anal command, Control R. The attributes, of course, are same we presented above. Now, let's compute factor scores. Let's compute factor scores. There is something we didn't do in the previous analysis. I'm checking now. Okay, we didn't perform the plot of factors. So now we must do it. So let's stop for the moment this new factor analysis. Let's go back again to the previous one, because there's something I want to show you. So we are here. So let's go back and perform again the previous factor analysis without rotation. Okay. So FA fact anal command, I attribute the output to FA, Control R. Now let's compute the scores and assign F the scores, Control R. And now let's plot the factor scores for factor 1 and factor 2, Control R. And the plot command was the command that I didn't run in the first part. This is the factor score, the scatter diagram between the factor scores, factor 1 on the horizontal axis, factor 2 in the vertical axis. Since the two factors, I remind you that the two factors are uncorrelated, the dots are distributed in the scatter diagram without showing a linear direction and without without being a line on a straight line. So after that, this is the correlation between the factors. The factors are, as said, uncorrelated. Control R. The correlation is 0. Okay. The means of factor 1 and factor 2 are also equal to 0. Control R. Okay. And the variances are equal to 1 because the factors are, or at least approximately equal to 1, because the factors are standardized variables. Okay, now we can go on and again repeat the factor analysis, the fact anal command in order to perform the factor analysis with the rotation of the factors. So let's select the command, Control R. Now let's assign the scores of the rotated factor analysis to the f.rot. F.rot is the object that represents the factor scores of the rotated factor analysis. Control R. And f.rot is the matrix, the 20 times 2 matrix of factor scores. Okay. So these are the new variables in our data set, and these are the values taken by these two variables unit by unit. Now, let's perform the plot again But I want to represent the new plot, the plot of the new factors, the rotated factors, with a different color, and add this scatter diagram in the previous one. I remind you that to do this, if I perform a new plot command, I lose the previous graph, and the new graph will replace the previous one. In order to avoid it and to add the new plot into the previous one, I have to use the par command, par, and the argument new is equal to true. So par new equal to true, Control R, and now let's run the plot command. So plot f dot rot, because now we want to represent the rotated factors, 1, and f dot rot 2. First column and second column of f dot rot command. The size of the dots 5 is okay. The label, so the title of the horizontal axis is factor 1, okay. The label of the vertical axis is factor 2, okay. And we can change the color into red, for example. Now let's select the command, press Ctrl R. So this is the new scatter diagram. The new scatter diagram is the red one, and it is overlapped to the previous plot, the previous scatter diagram represented with blue dots. As you can see, that it is evident that the new data set, the new graph is very similar to the equivalent to the previous one, but it is rotated. For example, let's consider these 4 dots. 1, 2, 3, 4 blue dots. They correspond to these 4 red dots. Okay, look at the pointer here when I'm using the mouse. These 3 dots, these 3 blue dots correspond to these 3 red dots, and so on. This blue dot corresponds to this red dot. This blue dot corresponds to this red dot, and so on. So basically, there's a rotation. In this case, a clockwise rotation of the cloud of dots, and basically it is equivalent to a rotation of the axis. So in this plot, I keep the axis unchanged or almost unchanged, and I do a rotation of the dots, but it is equivalent to keep the dots fixed and to rotate the axis. In this case, there is a rotation, but also a small translation of the axis. But the main idea is that the information does not change. So the cloud of dots does not change. What is different in the red dot, in the red plot with respect to the blue one, is that we did a rotation of the axis. We moved the axis, so the coordinates of the dots are changed, but the structure of the dots is the same. So the dots are not changed, basically. We can say that this is another way to look at the same phenomenon, at the same information, and we can say that we are looking at the same information from another point of view. Okay, this is the idea of rotation, and the consequence of rotation is that the new lambda values, the new coefficients used to express the original response variables as function of the factors are now changed, and few of them should be far from 0, and many of them should be close to 0. Usually, this is a typical consequence of the Varimax rotation, and this is useful to facilitate the interpretation of factors, to facilitate the understanding of what the factors represent. Let's go on. So this is the plot. Now let's check whether the new rotated factors are uncorrelated. I change f with f dot rot here, and again f with f dot rot here, and I compute the correlation between the first column of f dot rot and the second column of f dot rot. So factor 1 and factor 2 after rotation. I use 3 digits, 3 decimals, Control R. So the correlation is equal to minus 0.003, not exactly 0, but very, 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 very close to 0. So they are almost uncorrelated. Let's compute the mean values for factor 1 and factor 2 in order to check whether the factors have mean equal to 0. We use again 3 decimals or 3 digits, Control R, 0 and 0, the mean values. And let's compute the variances of the rotated factors. F dot rot, first column and second column, Control R. The correlation, the variances are equal to not exactly, but approximately equal to 1. So we can say that the rotated factors are also the rotated factors are standardized variables too. Let's compute the lambda dot rot matrix of new lambda values, so new loadings, factor loadings, with the usual command where we assign the FA dot dollar loadings to the object lambda dot rot. Let's assign these values, Control R, and now let's see the lambda dot rot values. Okay, this is the new matrix of loadings, the new loadings. So the new original response variables and the two, in this case, rotated factors. Again, this is not so evident, but it is at least more evident than in the previous case, in the unrotated case. Factor 1 is positively and highly correlated with punctuality, network coverage, and time. So with the evaluation of the customers about the punctuality of the buses, the network coverage of the bus service, and the timetable of the bus service. And it has negative correlations with the cleanliness and comfort, but the loadings are not so far from 0. So I think that we can consider these negative correlations as non-relevant. What about factor 2? Factor 2 is positively and highly correlated with the evaluation about cleanliness and about comfort, mainly about cleanliness, but also about comfort. 0.947, 0.609, the two loadings, so the two correlations. And the correlations of factor 2 with the other original response variables are not so far from 0, are quite close to 0, so they can be considered non-relevant. It is evident that the rotational factor simplifies something, and it is evident that since factor 2 takes high values when the evaluation about punctuality, network coverage, and timetable take high values, and vice versa. It takes low values when punctuality, network coverage, and timetable, the evaluation about punctuality, network coverage, and timetable take low values. Then we can consider factor 1 as quality of the bus, of the bus itself, quality of the car, okay, of the transportation mean, quality of the bus service, quality of the service, because it is correlated with the punctuality of the buses, with the network coverage, and with the timetable, okay? So factor 1 is satisfaction for the bus, the transportation service, transport service, okay? Factor 2 is highly and positively correlated with the evaluation for cleanliness and comfort. So we can say that factor 2 is the evaluation of the bus, the evaluation of the car, evaluation of the transportation mean, okay? In particular, the evaluation of the cleanliness of the bus and the evaluation of the comfort of the seats, okay? So this is the typical example of factor analysis where a multidimensional phenomenon, in this case, the multivariate satisfaction of customers of a bus service can be summed up by considering only 2 variables instead of the original 5 that represent the satisfaction as a bivariate phenomenon. So a multidimensional one only with 2 dimensions, the satisfaction for the transport service and the satisfaction for the car, for the bus itself. Okay. Let's go on. Let's go and put the correlations between the original response variables and the factors, but considering the f.rot matrix. So we consider the factor scores of the rotated factor analysis, of the rotated factors, and in order to check whether these correlations correspond to the loadings, the factor loadings. Let's select all the core commands, Control R, the correlation between cleanliness and the rotated factor 1 minus 0.313 correspond to the factor loading of cleanliness with respect to factor 1. The correlation between cleanliness and the rotated factor 2 is equal to 0.950, etc. And the factor loading of cleanliness with respect to factor 2 is equal to 0.947. So again, very similar value, approximately same value. Okay, and so on. So all the correlations correspond to factor loadings. This is confirmed. Now again, let's initialize the U matrix of the values taken by the unique factors, Control R. Let's compute the values taken by the unique factors, Control but we have to use f dot rot in this case, and the lambda dot rot. Control R. These are the unique factors. Again, the mean value the mean values of the unique factors are equal to 0 in all the cases. Before the computation of the communalities, let's consider another aspect that we didn't consider in the previous analysis. The G matrix. I remind you that the rotation of the factors consists in the multiplication of the matrix of factor loadings and of the factor scores, or the matrix of factor scores of a G matrix, the so-called rotation matrix. So this is the explanation of what we did in terms of rotation. I showed you what's the consequence from the geometrical point of view, considering the plot, and from the computational point of view, considering the output, the factor loadings and the factor scores. But what happened from the point of view of matrix algebra? From the point of view of matrix algebra, we have found a rotation matrix and multiplied this rotation matrix by the matrix of loadings and the matrix of factor scores. The matrix of loadings, the matrix of the rotation is an orthogonal matrix. In other words, the transpose of this matrix correspond to the inverse of this matrix. So let's add a comment, rotation matrix, and let's assign the values of rotation matrix to the object G. So G is equal to FA dollar rot max. So rot max is the attribute that corresponds to the rotation matrix. Control R. Let's type G, select Control R. No, there's something wrong. Let me check. Rot max. Sorry, not rot max. This is not a maximum, it's a matrix. So G equal to FA dollar rot max. Select Control R. Select G, Control R. This is the G matrix, the rotation matrix. It's a 2 times 2 matrix. This is an orthogonal matrix because the product between G and the transpose of G correspond to the identity matrix. So by definition, the transpose of G corresponds to the inverse of G. So G percentage star percentage transpose of G, this is the product between matrices, percentage star percentage, and the two matrices are G and it's transposed. Select Control R. This is the output of the product, a matrix with ones in the main diagonal and zeros, or approximately zeros, in the secondary diagonal, because in the element in first row, second column is 1.11 times 10 to the power of minus 16, and the element in the second row, first column is equal to 1.11 times 10 to the power of minus 16, same value. So ones in the main diagonal, zeros elsewhere. This is an identity matrix. So G is an orthogonal matrix. Now we have computed the lambda dot rot values and the f dot rot values, scores. So now I remind you, lambda dot rot values, let's control R, are these values, factor loadings of the rotated factors, rotated factor analysis, and if we compute the product between the lambda matrix, the original lambda matrix, the corresponding to the unrotated factor analysis, and G, the G rotation matrix, control R, we can obtain this 5 times 2 matrix, because lambda is a 5 times 2 matrix, G is a 2 times 2 matrix. The output is a 5 times 2 matrix, and the output corresponds to the loadings of the rotated factor analysis. Okay, so this is what we did in order to rotate the factors. We have found an orthogonal matrix G such that the new lambda values in the rotated factor analysis correspond to the product between the original matrix of lambda values, the original matrix of loadings, and matrix G. Okay. Now F, this is the matrix of the scores of the factors in the unrotated factor analysis, and F dot rot product between the F dot rot matrix and the transposed of G, or equivalently the inverse of G, control R, correspond to the F matrix of values, F scores. See that you have exactly the same values. So we proved the relationship between the G matrix, the rotational matrix, and the new factor scores and the new lambda values, the new factor loadings. Now let's compute the communalities in order to see the consequences of the rotation in terms of communalities here. So let's compute h1.rot, the communality of cleanliness with respect to the rotated factor analysis, lambda dot rot. So the communality with respect to cleanliness in the rotated factor analysis is h1.rot, and it is equal to 0.995. H1 was equal to 0.995, so unchanged. Now we don't need to compute again the unique variance. Okay, we don't need it. Similarly, let's compute h2.rot, the communality in the rotated factor analysis with respect to the rotated lambda values, the factor loadings. Control R and h2 dot rotated, the cumulativity in the rotated factor analysis is equal to 0.531, and h1 control R is also 0.531. Same, so cumulativity doesn't change. Again, h3 dot rot, sum of lambda dot rot values, h3 dot rot output h3 dot rot and h3. Let's compare it with h3, same value, so communality does not change. Also in the case of network coverage. Finally, h4 dot rot as a sum of the lambda dot rot values squared is equal to control R 0.387, and the previous communality was exactly equal to 0.387. And finally, h5 dot rot, the communality of factor analysis corresponding to the evaluation of timetable in the rotating factor analysis. Control R, h5 dot rot, control R is 0.569 and so on. h5, select control R was exactly equal to the same value. So the rotation of the factors with the Varimax method provide a new factor analysis, new loadings, new factor scores. It consists in the use of a rotation matrix G, orthogonal rotation matrix, so such that the transpose of G is equal to the inverse of G. That is multiplied by the factor scores and the factor loadings in order to detect the new factor scores and the new factor loadings in the rotated factor analysis. The consequence is that the proportion of original variability is the same. The proportion of explained original variability of the original response variables is the same for the rotated factor 1 and factor 2, but the interpretation of factors is simpler, is clearer, is more evident. So now it is evident what does factor 1 represent, what does factor 2 represent, and we can replace the 5 original variables about customer satisfaction, customer evaluation of the different aspects of the bus service with these two new variables, factor 1 and factor 2, that represent the evaluation of the customers, so the customer satisfaction, but only as a bidimensional phenomenon with only 2 dimensions instead of the original 5. For today, that's all. Next time we will go on with the new topic from the theoretical point of view. We will talk about composite indicators, a topic similar to factor analysis and principal component analysis, because the focus is on the variables, and we want to sum up the information of different variables. And we will go on with exercises in R for the application of factor analysis and principal component analysis. See you the next lecture. Bye-bye.